I'm the president of XL Orbital, and as luck would have it, I'm also the head technologist. So what I'm going to show you today is technology that I developed over the course of the last 10 years. But to give you a little bit of background on who I am and what I've done, I started XL Orbital when I was 25 years old, and I started it as an orbital welding company. And for those who don't know what orbital welding is, it's a type of welding that's used to weld together things like propulsion systems on satellites, rockets, aircraft, also to assemble semiconductor process machines. Much of what we did was in the semiconductor industry. Now, during the time that we were building orbital welding equipment and developing that technology, I thought it'd be a good idea to develop a type of orbital imaging system. You do a weld around the tube, it would be nice to be able to inspect it, because what traditionally is done is X-ray. And X-ray was not well suited to do that, because you could be doing a very miniature system and then you have to remove the production of that welded system from the manufacturing line, take it to what they call an X-ray monolith, or a large room where they do X-ray, and shoot X-rays of these tiny welds and look for tiny imperfections in the welds. And so, not very cost effective, it stops production, it adds an incredible cost to manufacturing these propulsion systems. So, I set out to develop a type of orbital inspection system that would go around the weld after it was made and certify it. Look for things like porosity, inclusions, or cracks. And so that's where all of this began, and that began about 10 years ago. And it's been a long and sometimes difficult road between then and now, and the development still continues. There's a lot of potential, I believe, with this technology. And as you look at it today, I think you may even come up with some ideas of your own. During my presentation, I'd like to keep it a little bit more casual. If you have a question while I'm at a slide, go ahead and jump in and ask me the question, because it's sometimes easier than going back in the slides and addressing it then. So just raise your hand, throw something at me. But I have sort of a unique qualification to talk to you today that some of you perhaps don't have. And that is, I was a big nerd as a kid. And actually, if I look out, among you guys, I think a few of you may have been also a nerd. And I know what you're thinking. He doesn't look much like a nerd. So there I am. And there I am at the science fair. So it doesn't get any more nerdy than that. Here's my glasses. They're pretty thick. I had a pen in my pocket. You can't see it, and I did own a pocket protector, but I didn't have it. So I'm going to superimpose that in the next slide, I think. Slightly out of date hairstyle. This is in the 80s when big hair was in style, so that didn't fly very well. And there is the coup de grace. I'm holding my science project, which is a hovercraft. So proof positive that I'm a nerd, probably a bigger nerd than anyone else here. I'm going to start with eddy current, not because this technology is eddy current, but because I think it's a common footing for everybody to start from. Does everybody here know what eddy current is? Most people here? All right. With eddy current, you basically have an oscillating magnetic field being induced by a coil, and you monitor that magnetic field, and you present what's called an impedance plane display. And in that sort of display, you have resistance on one axis, inductive reactance on the other, and it's a simple, calculating the hypotenuse of the triangle. And in this display, you'll have a scope that will have a memory feature in the scope, and the angle of this impedance will change relative to what's underneath the sensor. So that's basically what eddy current is. Our sensor is a bit different. We have two coils, many eddy current sensors do, They're arranged in what's called a reflection type arrangement, where you have a transmit coil and you have a receive coil. And you induce a magnetic field into the object that you're interested in, and the returning magnetic field is then intercepted and analyzed by the receive coil. That happens to be a picture of our sensor, common sensor. It's about 80 thousandths in diameter. And that's 80 thousandths, there's a laser pointer here, here we go. Okay. 80 thousandths is that central portion. The housing is bigger, just because we have a larger instrument that we mount it in. The reason why our sensor is different is because in order to describe it, I'm not going to describe it in terms of eddy current, I'm going to describe it in terms of transformer. And in a transformer, again, you have a transmit and a receive, or a primary and a secondary coil. And each of those coils has its own resonant frequency. And that resonant frequency is defined by this equation here, a very simple equation. And if you were to do a frequency response curve of, say, the sensor that I just showed, it would look something like this, where you would have one resonant frequency for one coil, a second resonant frequency for another coil. And because you have these two resonant frequencies, they quite often form this sort of M shape. And that's why I call it M wave, because it makes an M shape. But there's something very special about this M shape that I want to talk to you about. This particular transformer isn't just a simple step up or step down transformer. As you would imagine, the turns ratio determines the amount of voltage amplification you would have. For instance, if you have 10 turns in and 100 turns out, then you're going to get a 10-to-1 amplification of voltage. This transformer is a resonant transformer, meaning you will resonate one coil, you'll resonate a second coil, then you will bring those resonant frequencies or those resonant peaks close to one another. When you do that, you get this, what I call sympathetic response, and that is that it boosts the output signal quite a lot. 10, 20, 100 times, you'll get a huge amplification of your signal, and you'll be able to return a much more data-rich analysis by way of this amplification. So similar to a wine glass resonating when you run your finger across it, when you match the resonant frequency of something, it sympathetically vibrates, you get much more response out of it. So that's why I'm choosing to identify this sensor more in terms of a transformer than an eddy current sensor. It is subject to the same things that an eddy current is subject to. In other words, you send down an oscillating magnetic field into a conductor, it will have all of the characteristics of an eddy current, but we get more than that out of it.
So
yes?
It's very much like a TR metal detector, where it just basically
metal
it gets out of tune, and when you get metal, it gets out of tune, and
it's similar. It's similar, except this is much more powerful because we're not sensitive just to metal, we're sensitive to plastic. We can image your finger, we can image a glass. So it is similar in that you have the dual coil, and it's the dual coil does more to see a difference between the coils than a detuning.
Right.
Yeah.
So it's more bridge.
Exactly. So here, it's an interesting thing. We'll have these two peaks, and we use capacitance to tune the two resonant frequencies in much the same way that you would tune a radio. And you can see as the two resonant peaks converge on one another, you'll get an amplified output. This is showed in reduced format, but you can get hundreds of times of amplification using this method, depending on how you tune the circuit. The odd thing is, if you tune it exactly, if you put one resonant peak directly over the other resonant peak, there's almost a destructive phenomenon that takes place. You will not get peak output there. You get it when it's slightly out of tune. I'm glad nobody asked me why. Because I don't exactly know. In determining what makes the best sensor, we measure what we call Q. Q is quality factor, and basically Q is used to measure a lot of tuned circuits. But basically, we're using it to determine how much energy is transferred from one coil to the next. And just real quickly, at 3 dB below the peak voltage, we draw a line, and that represents the point at which the power is half, 3 dB down. Then we note the frequency 1 and frequency 2. That determines our bandwidth, and we basically divide the maximum volt, or the resonant frequency, the frequency at resonance divided by the bandwidth. That's the Q. You want a circuit that has high Q, high quality factor. But that's not enough. And you look here, we have a crack sample. And this is a sample that's made by NASA, and they put an EDM notch in a plate, and then they fatigue the plate until it propagates a crack from the EDM notch. And then they grind the surface, exposing only the crack. And that's important because you want a naturally occurring crack, more so than an EDM notch, to analyze some of this stuff, because you do get a different response. And if you run the sensor over that crack, which is 94 thou, it's a big crack, you'll get different responses depending on the frequency that you select that sensor to operate at. And I'll talk about that in the next slide.